Okay, let's get started. It's 8:10 already. So let me share my screen because I want to show you the new schedule. I edited it slightly. So I just edited it a couple of minutes ago. What I did is basically I moved graphical analysis of motion. It was in day 2. I moved it in day 3 because we haven't covered it in day 2. We just covered it yesterday. And exam was on Tuesday, but I thought that would be too rushed because we wouldn't have enough time to cover 2D vectors and 2D kinematics and projectile motion in one day and then take the exam. So I pushed the exam to Wednesday because Wednesday is a 2-hour class, so it's a good day for the exam to just have the exam and nothing else. And then day 6 would be continuing projectile motion, and for the rest of the lecture, we will have some problem solving and like a review session that would make you more ready for the exam. Does this new plan sound good? Okay. Does anyone have any conflicts with the timing of the exam on Wednesday? Okay, in any case, if you have any problems with the schedule or if you have any conflicts with the time of the exam, just email me and we can work something out. Okay, so that's for the logistics. Let's go now to the content of today's lecture. Let's first give a quick recap. I want to share my screen because this summarizes what we have learned so far. So, so we've been working with motion in one dimension, and this summary here gives basically all the equations and all the graphs we worked with. So for all motion, the definition of velocity, or rather average velocity, was the change in position divided by the change in time. So displacement over elapsed time. Here, the subscript x just denotes that motion is along the x direction. This will be relevant to us in a couple of minutes when we discuss motion in more than one dimension. So we will have both subscripts x and y to indicate different directions. That's why we added this subscript here. Then the definition of average acceleration is the change in velocity over elapsed time. Those are the general definitions. Then we have different kinds of motion. We have uniform motion, which is defined by constant velocity, in which case the acceleration is 0, and the equation is just x final equals x initial plus v delta t. There is no acceleration part because acceleration is 0. The graph corresponding to that is a straight line, the slope of which is the velocity, the constant velocity. If you would plot the velocity versus time graph and the acceleration versus time graph, you will have two horizontal lines. Velocity will be a positive horizontal line and acceleration will be just a 0 horizontal line. For motion with constant acceleration, this is the general case we discussed last time, for which we have the general 3 kinematics equations, 1, 2, and 3 here. The first equation gives us the velocity at any moment in time. So the velocity is a straight line, the slope of which is the acceleration, and the position is a parabola. It's a curved graph that goes as the square of the time. So equation 2 here is the equation that gives us this shape. And then we had one final equation for kinematics, in which we eliminated the time variable. So we chose the time from equation 1 and substituted it into equation 2, eliminated the time and rearranged to get an equation that doesn't have the time in it. So it just relates velocities and displacements with acceleration. So that was basically what we had, what we covered in the previous 3 lectures. Today, we want to do more than 1 dimension. We want to do 2 dimensions. But to do that, we need to be familiar with the language of vectors because, sorry, we need to be familiar with the language of vectors. Last time, we just denoted the direction with a positive or negative sign. But if we have more than 1 dimension, then positive or negative sign is not enough. We need a direction, we need an angle, we need a magnitude. So that's what we're doing today. So let me share my screen for the let me share my screen for that paper. There. Okay. Okay, so today's lecture 4. And the outline for today is the following. We have vectors and scalars in 2 dimensions. Under this category, we will discuss the graphical use of vectors, graphical use of vectors. In particular, we will discuss vector addition, and scalar multiplication. Then we will discuss again coordinate systems, but now we're going to discuss them in 2 dimensions. Coordinate systems, coordinate systems and vector components. Okay, that will all be graphical. Then we will do algebraic vector addition. Okay, good. Once we are done with this machinery, we will introduce kinematics in 2 dimensions. The next time we will discuss projectile motion, which is one particular example of kinematics in 2 dimensions. So let me just put it in here for completeness. So projectile motion. This will be next time. Okay, after we're done with this theory developing, we will go to Pivot Interactives as yesterday, and there is another virtual lab, which in this case is not really a lab, but rather a recitation-like activity, where you can play around with vectors, move them around, scale them, find the angles, so you get a sense of how vectors work in an interactive way. So this is the structure for today. Good. Let's start with vectors and scalars. So vectors and scalars. So as we discussed before, there are physical quantities for which it's enough to completely specify the system with just one number, just one unit, such as the time, temperature, mass. Those are scalars. But there are other quantities that also have a physical quality that indicates direction, like velocity. You need direction to know where you're going, not just how fast. Also displacement. You don't just want to know the distance between 2 points, but also where this distance is along. So you need more than just magnitude. You also need direction. So we define a scalar. So definition. So let's see. So a scalar physical quantity is described by a single number with a unit, of course, but no direction. But no direction. Examples are time, mass, temperature, etc. On the other hand, we have a vector quantity. A vector physical quantity has both a magnitude and a direction. So it's not enough to specify just a single number with a unit, but you also have to specify the direction in which it's going. So examples on that are velocity, acceleration, later on we will know that forces are also vectors, and so on. Okay, I know this we covered before and now we're repeating ourselves, but this is important to build in 2 dimensions as well. So a vector is represented by an arrow. So if you're going to represent a vector, let's say it's an arrow like this. It is anchored at some point and its tip points in the direction of the vector. So this is vector, let's call it vector A. And we indicate the vector to differentiate it from a scalar. We put a small arrow on top. So this is vector A. And it points in this direction. The length of the vector indicates its magnitude. So it's proportional to the magnitude. The length of the vector A is proportional to its magnitude. Okay. So for example, if we have another vector b that is anchored here, then the magnitude of the vector A is bigger than the magnitude of the vector B. To indicate the magnitude, we just put the vertical bars around the vector. So this is magnitude or length of the vector. And same thing here. This is the magnitude of B. Okay, good. Given vectors, we can add them, we can subtract them, and we can multiply them by scalar values. So let's see how to add two vectors. So this section is the graphical use of vectors. Graphical use of vectors. Vector addition. Okay, let's say we have two vectors, A and B, but not these two vectors above. I'll draw two new vectors just to have them in different directions. Let's say we have vector A pointing this way, A, and let's say we have another vector B pointing this way, and I want to add the two vectors. What I need to do is, well, there are two ways of adding vectors graphically. There is the head-to-tail approach, and there is the parallelogram approach. So let's start with the head-to-tail approach. I want to find A plus B vector, which I can call vector C. I want to find this vector C graphically. What I'm going to do is, let me just copy these to have them separately instead of do it again. Okay, so I move vector B comes to the head of vector A. So the tail of B is attached to the head of A. That's head to tail. That's where the terminology comes from. So head to tail. And then I draw a, sorry, and then I draw a vector that starts from the anchor of A to the tip of B. So from here all the way here. So this is vector C. So you can think of it as you walked a little bit until you went to the tip of A, and then you walked back until you went to the head of B. So effectively what you did is moving along vector C from the anchor to the head. So this is the head to tail method. There is another method. Just put this here. We have more space for the other method. The other method is parallelogram. Instead of moving the vectors around to be head to tail, we move them around to be at the same anchor. So the starting point becomes the same. So let's again copy these two vectors here. And I will move them. I will move one of them to be at the anchor of the other. So let's move this one here. Okay, so now they have the same anchor point. And then I draw a parallelogram. complete the parallelogram by drawing a parallel to vector A and a parallel to vector B, then the diagonal is vector C. Okay, this is the parallelogram method. Okay. You see at the end, vector C is the same. If you compare the vector you obtained here with the vector you obtained there, they are the same two vectors. They point in the same direction, they have the same length. So the two methods give us the same vector graphically. And we are free to move vectors around to do this kind of analysis. So they're not anchored at a specific point, at least in this simplified discussion. So we're free to move them around. So as long as the vector have the same direction, the same magnitude, we're declaring it to be the same vector as the other. Okay, good. Good. So let me give an example of vector addition. So example 1. So example 1, Bob is standing in a field next to a tree stump. He walks 200 meters due east, then 100 meters due north. So 200 meters due east, then 100 meters due north. So first, draw an overhead view of the journey, assuming the stump is at the origin. So stump is the origin, and we want to draw an overhead view. Draw an overhead view. Draw the net displacement vector as well. Okay. Draw the net displacement vector. So I'm going to call that delta x with a vector. So let's do that. So we have, let me pick the coordinate system to be a different color. Or let me draw the cardinal directions. Okay, so north, south, east, west. Okay, so 200 meters due east. Let's break our grid to be of units of 100. So this is 100, this is 200, this is 100, this is 200 meters. So Bob walks 200 meters due east. So that's this part here. This is the first part of his journey. And then from there, he moves 100 meters due north. So all the way here. So this is the second leg. This is the actual journey. This is where he started, and this is where he ended. Okay. Then draw the net displacement as well. The net displacement is then, this is already head to tail, so the net displacement is this one. And this is effectively where Bob walked. Okay, so this is the picture. The second part of the example asks, how far away is Bob from the tree stump or from the origin? So basically, how far is this? So we want to get the length of this vector, basically. So let me draw a larger picture here. So we have a triangle. Triangle of vectors. So, and we want to let me call these A, B, and C. So basically what we want is the magnitude of C. Calculate the magnitude of C. Because this is basically the distance from the final point to the initial point. This is how far away is Bob from the tree stump. So okay, we know that the magnitude of A is 200 meters. We know that the magnitude of B is 100 meters, and we want to know the magnitude of C. This is easy because this is Pythagoras theorem. This is a right angle triangle. So this is just C squared is equal to A squared plus B squared. So 200 meters squared plus 100 meters squared, and then you take the square root of that, so gives you that C is equal to, when you calculate that, you get 223.6 meters. Okay? This is effectively this is the distance from the origin to where Bob ended. So instead of walking 300 meters in total, the path length that he actually covered, he could have just walked straight from the initial point to a final point in a straight line and only covered 223.6 meters instead of the 300. The third question says, if Bob had wanted to go directly from the tree stump to where he is now, what direction should he have walked in to go straight there? This is just asking about the angle here. When you are asked about direction, this is basically asking about the angle of the vector. Because if Bob wants to go back to the tree stump just in a straight line, he has to go along this vector here. So the direction is indicated by the angle this vector makes with the x-axis. Okay, so to do that, we can do trig. This is again a right angle triangle. So I can use the tan of the angle as the opposite over adjacent to get the tan of the angle. So tan theta is opposite over adjacent. In this case, it is the magnitude of the vector B divided by the magnitude of the vector A. So 100 meters divided by 200 meters, the units cancel and you only get a number, you get a half. So if tan theta is a half, you can reverse that and say theta is the inverse tangent of half. And you can find that on your calculator to be 26.6 degrees. what we have done here is very systematic and will happen over and over again. We will have components of a vector. In this case, they are the vectors A and B. These are the vertical and horizontal components. And then you would want to find the distance or the magnitude of the resultant vector and the angle it makes with the horizontal axis. This will be very standard, and we will formalize it now. So this was just an example you can imagine, like someone is traveling east and then north. So you want to find the full distance, and then you want to find the direction. So this was tied to a real life example. We can now formalize the discussion. But one final thing is that, okay, so this was an example of a vector addition. Now we can do one more operation on vectors, which is multiplying them by scalars. So multiplying, or let's say scalar multiplication. Okay, let's say you have a vector A. And this vector is like this, vector A. You can multiply this vector by a scalar, let's say 2A. Let's say vector B is defined as 2A. Okay, this is a scalar multiplication. This just says double the size of vector A, but keep the direction the same. So as long as you're multiplying by a positive number, you keep the direction the same. So this vector B is like this. It's twice of vector A. So vector B, and you can think of it as vector A twice. Yeah, that didn't fit, so let me. Yeah, so this is vector B. It's two vectors A stacked on top of one another. So it is 2A. We can also have another vector C that is negative A. Multiplying by a negative sign makes the vector reverse direction. So let's take that vector again and multiply it by a negative sign. So, oh, yeah, never mind. Okay, so this is the vector C equals negative A. Same magnitude, but direction reversed. If instead you have negative 2A, then you reverse direction and then enlarge the vector twice its size. So this is what scalar multiplication does. It scales your vector and reverses direction if the sign is negative. Okay, so far so good. Does anyone have any questions so far? Okay. If you don't have any more questions, let's discuss coordinate systems. So yeah, so far in our outline, we did this one, and this is the one we're at. So coordinate systems and vector components. coordinate systems and vector components. Okay, so before we introduce a coordinate system as a line with an origin, and then either positive to the right or negative to the left, indicated the direction. But now we want to move in more than one dimension, so we have to have a grid, a full grid. So we're going to use the familiar rectangular Cartesian coordinates that involve two perpendicular axes, x and y. So we're going to have an x-axis and a y-axis. Those are perpendicular. And then it's a grid, like so to describe the location of a point, you need two numbers. You need where it is on the x-axis and where it is on the y-axis. For example, this point here, if I want to specify its location accurately, I can say it's 2, 2, because it has 2 units along the x-axis and 2 units along the y-axis. This point, on the other hand, only 1 unit along the y-axis, but negative 2 units on the x-axis, so negative 2 and 1, and so on. So you need two numbers. Vectors are essentially the same. We just have the vector itself, and we specify the vector by its components along the x and y axes. So let's do that more formally by having a vector point like this. So it's an arrow that starts at the origin and ends at some point, and let's call this vector A. Vector A. Okay. Its components are AX, AX, A sub X to indicate the X direction, and A sub Y. Okay. You can see from the parallelogram rule that we discussed before that A is the sum of these two components because you point them, you anchor them all at the same point, and then you draw the diagonal. The diagonal is the sum. So A is equal to AX plus AY. Okay, so we have broken vector A to its two components, two component vectors, a component vector parallel to the x-axis and another component axis parallel to the y-axis. Okay, so AX is the projection of A along X, and AY is the projection of A along Y. Okay, so let's say this is vector component or component vector, component vector, X component vector, and this is Y component vector. Good. So this is vector decomposition. We're going to do this a lot. We're going to do this many, many times, especially when we do forces and free body diagrams. all equilibrium problems and all free body diagrams, you must decompose vectors into parallel components and perpendicular components. So this, like, you really need to get familiar with this language and with how to decompose a vector. So this is worth solving. This is worth covering a little bit with more detail. Okay, good. Instead of the component vector, we can, so we have vector AX here, for example. It's pointing 2 units along the x-axis, and it's only along the x-axis. So we can define a scalar number, a scalar quantity that tells us the size of the vector, and then encode the fact that it points along the x direction by the subscript or by a unit vector. So let's see how to do this. So AX is 2 units along positive x axis. Okay? So we can find that follows. So we can say AX component vector is equal to 2 times x hat. This x hat is a unit vector along along positive x-axis. It uses the idea of scalar multiplication that we discussed a couple of minutes ago, that you can make any vector out of little pieces. So in this case, the point vector x hat, let me use a different color. It's going to be this one. This is x hat, and this is another x hat. So 2 of x hat will make up ax. So we define 2 unit vectors, 1 unit vector along the x-axis and 1 unit vector along y-axis. So unit vectors define unit vectors x hat and y hat. This little hat is just a special symbol to indicate that it's a unit vector instead of drawing arrows as we did with the actual vectors that don't have unit length. So magnitude of x hat is equal to 1 by definition, and magnitude of y hat is also equal to 1 by definition. Then you can write any vector as a combination of these units. So in general, you can write a vector A as a scalar ax along x hat plus a scalar ay along y hat. Let's give an example on that. So let's say we have our vector as A is 3x hat plus 1y hat. How am I to draw this vector? I design my coordinate system. X and Y. And then I also design the grid. Let's say like this. And let's say these are the y grids. Okay, so x hat is just a vector, a unit length. So x hat is just one unit. Okay, so if I have three of them, then I have x hat, x hat, x hat. So I have this full vector here as the component vector. This would be a sub x. And then I go one component of y hat. So y hat is the same way as this way here. This is y hat, and I only have one y hat. And then you add them, vector addition like we learned. So this is head to tail. So you can do this here, and this will be your vector. This is your vector A. So it is composed of 3 units along the x-axis and 1 unit along the y-axis. And this is what this notation means. Okay. Let's say we had a different vector, vector B, and this vector B was, let's say it was negative 2x plus 2y. Again, I will do the same thing. The negative sign reverses direction. It's a scalar multiplication by a negative, so it reverses direction of x. So that gives me 1 unit here, another unit there. So the full unit is 2 units to the left. And then I go up 2 units. And I then add the 2 vectors. Sorry, I wanted to, go up 2 units. 1 unit here, 1 unit there. Then it's head to tail. So that gives me the following vector here. This is vector B. Okay, so you can write any vector pointing in any direction using these unit vectors. So in general, we write this like this as a sub x and a sub y along the unit vectors, and then we absorb the positive or negative sign in the scalar multiplier itself to indicate whether the unit vector flips sign or not. Okay, good. Okay, given that we have the vector decomposed, how do we get its magnitude and its direction? How do we get the length and angle it makes with the x-axis? So this is one representation of a vector. This is called the vector component form. This is vector component form. But then we may want to have the magnitude and direction form. Sorry, give me a second. Okay, so we were saying that we want to get the magnitude and angle form of the vector. So let's again have a general vector here. Let me copy this grid instead of doing it over and over. And let's say I have a general vector. Let me erase these vectors. Okay, let's say I have a vector pointing this way, vector here. This is a vector A. Okay. I want to know its magnitude, its length, and its direction. Magnitude is just the length of the arrow. Direction is the angle, theta, the angle it makes with the positive x-axis. Counterclockwise. This is just by convention. So you start from the x-axis and you go counterclockwise. So this is the angle theta the vector makes. Okay. In terms of its components, this vector can be written as ax and ay here. So this would be ax, this would be ay. And now I dropped the vector rotation because I'm talking about the components, the lengths, and the direction is encoded in the unit vectors. So I'm only talking about the components here. So Pythagoras' theorem, this is a right angle triangle by construction because the components are parallel to the x and y axes, which are perpendicular in this coordinate system. So the length of the vector by Pythagoras' theorem is the square root of ax squared plus ay squared. Okay, this is the length, the vector. You just get the two components of the vector, and then you square them, add them, and take the square root. For the angle, we have the tangent, tan theta, is opposite over adjacent again, opposite over adjacent, which is equal to ay divided by ax. So if we have any vector in component form, we can convert it to magnitude and direction form by simply doing these two rules. Okay, good. What if we want to do the reverse? What if we are given the magnitude and angle and we want to get the components? Well, let's assume we have the vector here. Sorry. This is the length of the vector. This is a right angle triangle. This is ay, this is ax, and this angle is theta. And I don't know what ay and what ax are. I want to find them in terms of the length and angle, assuming that I know the length and angle. So assuming A and theta are given, what is AX and AY in terms of them. We are going to do trig again, but instead of tan, we now want to relate the sides to the hypotenuse. So we need to use either sine or cosine. This is a good time to refresh your memory on trig because we're going to be using it a lot. So sine of theta is equal to opposite over hypotenuse. I don't know if I wrote the word hypotenuse correctly, but it doesn't matter. So the opposite here is AY. The hypotenuse is magnitude of A as a vector. We can then rearrange this by multiplying both sides by magnitude of A. So we get AY is equal to magnitude of A times sine theta. So assuming we know the length and angle, we can just multiply the length by sine of the angle to get the y component. And if we want to get the x component, then we need the adjacent. So cosine of the angle is the adjacent divided by the hypotenuse. This is AX divided by the length, hypotenuse. Again, multiplying by the length in both sides, we get AX is equal to A cosine theta. So these are the two pictures going back and forth. If we have the components, we can use these two equations to calculate the length and direction. And if we have the length and direction, we can calculate the components by using these two relations. If the angle is the angle made counterclockwise from the positive x-axis. If it's a different angle, you will need to do the geometry again and use trig the way we did here. Okay? Good. So let me give you a quick example or a quick in-class example before continuing this, just as a just as an exercise. I don't know why I'm losing words today. So example, say in class for you to do it. Okay, so let's do the example together, and then I will give you one final discussion on algebraic addition of vectors, and then we are gonna do the lab. So share my screen. Okay. So we have a plane flying at 500 miles per hour. So the speed or the magnitude of the velocity is 500 miles per hour. Okay. And it's going at 60 degrees north of east. So let's draw that. Let's see what that looks like. So here are our cardinal directions. North of east, that means start east and go north. So we start east and go 60 degrees towards north. So 60 degrees until you get there. That's 60 degrees, okay? And go for a length of 500 miles per hour. So this vector is 500 miles per hour of length, okay? This is the vector. So this is vector V, and we want to get its X and Y components. So you can draw the triangle as usual. This would be the X component, and this would be the Y component. We know the hypotenuse and we know the angle measured from the x-axis. So Vx is simply the magnitude of V times cosine the angle. I'm calling it theta 1 because that's problem number 1. This is 500 miles per hour cosine 60, and that's just 250 miles per hour. Okay, good. Then the y component is V sine theta 1. That is equal to 500 miles per hour sine 60. That is 433 miles per hour. Okay, those are the components. If we want to write a vector completely, that would be V equals 250 miles per hour in the x hat plus 433 miles per hour y hat. That is the vector component form. Okay. The second case tells you that instead the plane is flying 60 degrees south of east, not north of east. So in this case, part 2, theta is 60 degrees south of east. This is not the standard angle we are used to measure because we said we want to measure counterclockwise from the x-axis. So our formulas will be a little bit different. But let's draw that anyway. East, north, south, west. We start from east again, but south of east. So we go all the way here south until we get to 60 degrees. So this is 60 degrees south of east. The length of the vector is still 500 miles per hour, didn't change, but the direction changed. So now this is the x component, and this is the y component. Okay. So our formulas that we derived earlier were only when the angle was measured from the x-axis counterclockwise. So if you want to stick to that angle, you can get the equivalent angle of that vector, which would be 300 degrees. But there is a much easier way, which is just to get the length and indicate the direction independently by a sign. So get the length of Vx. Vx is still the same. It is the magnitude of V times cosine of this angle theta 2. This is the same, still 500 miles per hour. Cosine 60. That is still the same, didn't change, 250 miles per hour. And it makes sense because the plane didn't change its direction along the x-axis. It's still going to the east. But for the y-axis, we see it flipped its direction. So Vy, we can still get the length as V sine theta, but we add a negative sign to indicate the change in direction. So V sine theta 2, that's equal to negative 500 miles per hour sine 60, which is equal to negative 433 miles per hour. If you didn't include the sine, but instead used the angle 300, you will still get a negative number. So you can just write it as V sine theta, but add theta to be 300, and you will get negative 433. You just need to be consistent. If you want to use the equations we derived, you have to use the angle measured counterclockwise from the positive x-axis. If you want to stick to your intuition, you can just draw the relevant triangle and do trig every time you want to do it. Which, like, I prefer to do it every time by drawing the triangle, because that makes it much less possible to make mistakes. In component form, this becomes 250 miles per hour along x minus 433 miles per hour along y. So it looks exactly the same vector, but with a minus sign instead. It will have the same length, exactly the same length, but it has a different direction. And that tells you that speed is not the full story, because in both cases, the speed is 500 miles per hour. But one is going in a certain direction, the other is going in a completely different direction. So that's the difference between speed and velocity. Good. That was all graphical description. So we can also do vector addition algebraically. So algebraic vector addition. Let's say we have two vectors A and B, and we decompose them into component form. So AX along X hat plus AY along Y hat. And for B, we have BX along X hat plus BY along Y hat. And we want to find the vector vector C, which is the sum of A and B. So C is defined as A plus B. We did that using the head-to-tail method, and we did it using the parallelogram method, but we can also do it algebraically if we have components. So what we do is that we add each component in this direction. We don't mix components. So the Cx component would be A sub x plus B sub x. And the y component would be A sub y plus B sub y. So the final result would be that the vector is AX plus BX in the x direction plus AY plus BY in the y direction. Very straightforward. You just add the corresponding components in the corresponding directions. You just need to be careful not to add different components because they point in independent directions. The beauty of this algebraic expression is that it's not just restricted to two vectors. You can add however many vectors you want. Like if we have another vector D, which is A plus B plus C, you can add all the corresponding components, and in X and Y direction, you will get a result that is consistent. Okay? Okay, so that's it for vectors. The reason why vectors are important, the reason why we spend some time doing them, is that when we do two-dimensional kinematics, we will basically have two directions for motion. Like, let's say you throw a ball at an angle. The ball is moving horizontally and vertically, like it goes up and it goes forward. So you need to address both directions of motion. And in this case, we have generalize our definitions a little bit. So displacement becomes a vector, a two-dimensional vector. It's always a vector, but it becomes a two-dimensional vector. And we denote it by delta r instead of delta x, just not to confuse our x and y. And that becomes the displacement in the x direction plus the displacement in the y direction. Okay? And velocity becomes a vector that is velocity in the x direction plus velocity in the y direction. Same thing for acceleration. Acceleration becomes acceleration in the x direction plus acceleration in the y direction. And then the kinematic equations become two sets of equations. They are the same equation, you just have two multiplets of them. So V, we originally had V final equals V initial plus A delta T. Now we need subscripts X, 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 because now it's along the X direction. We have delta X equals V X initial delta T plus half AX delta T squared, and V final squared X, right, X equals V Y final, X plus 2AX delta X. Those are the three kinematics equations that we spend some time with. But then you have another set of equations in the other direction. So this is Y, 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 Y. So these are the kinematics equations in two dimensions. It's just two copies of one-dimensional kinematics. And then projectile motion, for example, you have the source of acceleration is gravity. So the acceleration is purely in the y direction, in the vertical direction, but there is no acceleration in the x direction if we ignore air resistance. So you get ax equals 0, but ay is equal to negative 9.8 meters per second squared. So you have different, like, these two are completely independent. The only thing in common is the time elapsed. But completely independent motion. So independent, so let's say x and y directions are independent. Okay, that's why we spend some time doing vectors, because now we're gonna use them when we do 2D kinematics and projectile motion. Everything generalizes in a straightforward way. You just have an extra component to what you already had. Okay, that was it for the lecture today. If you have